Okay, in this video, we will do a brief revision on uncertainties. I will focus mainly on the identities and not the actual measuring technique that you need for paper 3. That one another day lah, another video. So you should know how to read vernier calipers and micrometers. You should know the type of errors, systematic and random errors, and how to decrease them. And we're also going to focus on the uncertainties and identities. Okay, so do try some past years. I will find the past years in the Google Drive link that I will share with you in the main message. Okay, so we're going to look at an example. Let's say the length of an object is 4.56 plus minus 0.02 cm. So when we include uncertainties or error, we would use it as plus minus 0.02. Okay, so there's this thing called absolute uncertainty. The symbol that we will use is delta x. And this absolute uncertainty tells us like, oh, when we take a reading, we should probably get 4.56, but the range that is expected is 4.56 minus 0.02 and 2 plus 0.02. So 4.54 to 4.58. So factors that affect the size of this absolute uncertainty would include the instrument that you use. Like if you use a micrometer, it has a smaller uncertainty than, say, a meter rule. So we will generally take the smallest division of your measuring instrument. Bear in mind, this one got a lot of nuances to this that I am not going to talk about here. You will have to do some past years. Okay. All right. And it also depends on the experiment setup. This is very relevant for you in paper 3 because sometimes in the best situation, we get the smallest division, but our measurement is rarely the best. So absolute uncertainty is 1 SF, very important. I will repeat this over and over. Second thing about uncertainty is percentage uncertainty, which is del x over x. So based on my example there, I'll take 0.02 over 4.56. Same unit, no need to convert. All right. So when you write absolute uncertainty, 1 SF, when you write percentage uncertainty, you should write your answers in 2 SF. Okay. If you don't follow the SF, highly likely you will lose marks. So this will be 0.44%. Okay. Percentage uncertainty, del x over x. You want to write it in percent times 100. Okay. So again now, be careful of the SF. And now we're going to look at different identities. Okay, so identities regarding uncertainties. So I'm going to give you a few general identities that is generally relevant for you right now. Let's say to find x, I take a plus b. So to find the uncertainty in x, I will sum up the uncertainty. So it doesn't matter whether it's plus or minus. As long as you take two readings, you add on the uncertainty. So if x is, again, this is multiplication. So when you multiply things, right, they might not have the same units. Like the unit for A, B, and C might very well be different. So we will divide by the actual reading so that the units cancel off and you get a percentage. So you notice that the percentage uncertainty of A, of X, is the total of the percentage uncertainty of A, B, and C. Okay? So as long as it's not plus minus, we are starting or we go into percentage. So what happens if, let's say, you have a to the power of n? Then you would just multiply the percentage uncertainty n times. Okay, this 3 is good enough. Okay, and this is very important. When you write your final answer, we care about this. Okay, so normally you already spend a lot of time doing some calculation and then you lose that mark because of this. It's a bit painful. So we'll go back to the example that I gave you just now, 4.56 plus minus 0.02. So normally we'll bracket and put cm at the back as units. Okay, same thing with prefix. So this absolute uncertainty must be 1 SF. I don't care what you do, the number at the back has to be 1 SF. And the number in front must have the same decimal point as the number at the back. So your actual reading has the same decimal point as your delta x or your absolute uncertainty. Failure to follow will lose 1 mark. That's all. Okay. So now we're going to try some examples. Uh, Again, this whole page will be have probably already been sitting in your OneNote for a day. Okay, so I want to talk a bit about estimating value. Sometimes you encounter questions like this, either in paper 1 or paper 2. When it comes to estimating, right, definitely write your answer in 1SF because you're estimating. If you tell me that the mass of the wooden rule is 3.445 kg, I'm like, how? What laser eye you have? So I don't know, I hold a meter rule, I think is 0.2. You might ask me how. I would say it's just experience. So it's 1 mark anyway. So you're just guessing or estimating. So let's say you think about a tennis ball, right? Then you're like, I don't really know what is the width of a tennis ball. So maybe you guess the diameter is about 8 cm. My hand here is about 8 cm. Okay, I actually have a tennis ball in my desk, but never mind lah. So you can estimate the radius is about 4, and then you plug it into the equation, 4 over 3 pi r cube. Okay, then you get around 300 cm cube. So normally this kind of question, they have a range in the mark scheme. Okay, so this kind of range, copied from the mark scheme for you, this would be 0.05 to 0.2 kg. And this range of acceptable answer, which I think is a bit small, is 50 to 300 cm cube. By the way, this one can ask anything, including the volume of a human head. Alright, anyway, here you have a metal wire length L, cross-sectional area. Volume is given by this expression. And then they measured the diameter, the length, and the mass of the wire. You are asked to calculate the density and the absolute uncertainty. So you need to do two calculations. You need to find the value of rho, density, and to find the value of delta rho, and write your final answer. Okay, so first thing first, I'm going to substitute V because density is mass per unit volume. So pi d square L over 4, bring the 4 up and multiply. And then I will substitute values. Okay. So generally when people here could make a mistake by not checking the units. If you look at the final answer unit is kg meter negative 3, meaning all these units have to be SI. So the diameter D, mm should convert to meter. Okay. So negative 3 and then 25 cm converted to meter negative 2. Okay. Don't forget the 0.225 gram as well. That should be converted to kilograms. Now, you will probably notice that you make a mistake, especially when your final answer doesn't make sense. Okay, so if you forget, it's worthwhile to stop and ask yourself, hey, does my answer make sense? Got logic or not? Okay, so right now, past me was pressing the calculator. I noticed that the answer looks a bit weird. So I'm checking my working. Okay. Generally, this kind of question, right, is a bonus. And I say it's a bonus because you kind of know what to expect. It's not like forces, they can draw any which way they want. And if you can do it, it's a lot of marks. It's at least like 4 to 5 marks. All right, so anyway, gram converting to kg. So it will be 10 to the negative 3 times kg, because negative 3 times 10 to the power of 3 cancels out. I know you like to divide by 1000. Learn to use prefix. Good students are very good at using prefix. It's kind of like how we identify strong students, you see. Okay, anyway, pressing the calculator, I'll get this value. And now I need to find the absolute uncertainty. So when I measure density, right, I include M, D, and L. So I have to include all the uncertainties. M, D, and L. But L I use 2 times because square, that's why I multiply by 2. Percentage uncertainty in M will be 0.01 divided by 0.225. D would be 0.01 divided by 0.38. And L would be 0.01 divided by, 0.1 divided by 25. Okay, so the sum up all the percentage uncertainty. If there is a power 2, then you multiply by 2. Okay, so just sum up. You don't care whether it's denominator or numerator. Okay, so generally, right, I will write out the percentage for each individual measurement. So for M, the percentage uncertainty is 0.44. For D square, or 2 times D, is 5.3. And you notice I've already written down in 2SF. Okay, and for L is 0.4%. All right, the reason why I isolate them is so that if there is a mistake, right, I should be able to tell that the percentage is either too big or too small. So totaling this up, I'll get 6.1, and I'll just take 6.1%, multiply by the actual value of density, 7936, and whatever number I get, like 487, I need to write in 1SF, which is 500. Must write 1SF. Okay, you write 489, I'm very happy. I'll minus 1 mark. Okay, so then the density here have to follow the decimal point of the one in front. Okay, so if you're wondering why because no decimal, both also don't have decimal point, why can't I write 7936? Well, because when you write them in standard form, one is 7.9 times 10 to the power of 3, the other one is 0.5 times 10 to the power of 3. So it should have the same decimal point. Same decimal point when written in standard form. That one you don't want to write standard form also can. Okay, you know this thing called like 个十百千万 or sa pulo ratus. So it's the same idea. You should maintain the same thing. Okay, let's look at this new question. You now have an analog voltmeter, okay, and we use it to measure potential difference across the resistor. So describe one example of systematic error. Okay, there's going to be some weird video editing thing here. So reasons for systematic error is errors that happen again and again all the time. So like zero error, or you use the instrument wrongly. Okay, random error is you view the scale from various angles at different times. You were distracted lah, you play your phone, then you just look at the scale differently lor. Random you cannot tell what will happen. Or maybe when you read the scale, let's say your brain when they read scale between 4 and 5, always jump scale 1. So instead of 4, 5, 6, you go 4, 6. It happens. Human error. Okay? So normally random error is due to humans. Systematic error is due to instruments. Normally. But don't write like that. You describe the thing properly. So part B, potential difference across the resistor is measured, and you have a resistor with the label of 125 plus minus 3%. 3% is the absolute uncertainty. So to find power dissipated in a resistor, we're going to use the equation V squared over R, because these two values are given. And V here is 5 squared, R here is 125. Okay. So once again, the plus minus, normally we write absolute uncertainty. Sometimes we can write percentage uncertainty. So anyway, the power dissipated here is 0.2. Calculate the percentage uncertainty. So what we want is del P, power over P. So we use volt 2 times because of the square, and then we use the resistor 1 time. So we take the percentage difference for delta V, 0.1 over 5 plus 3% of resistors. Okay. So whenever we perform a measurement, there's an uncertainty, we just total up the percentage uncertainties, unless they have the same unit. So if in this case you have 7%, the percentage uncertainty is 7.0%, right into SF, okay? All right, now you're asked to find the absolute uncertainty. So we know that the percentage is 7%, so the absolute will be 7% of 0.2. And this one would be 0.014. So again, 1SF, so this would be 0.01, and 2 decimal point, right? So we're going to follow 0.20. Any mistakes regarding SF and DP will lose you 1 mark. So let's not lose that kind of mark lah. All right. I feel like the computer got glare on my face. Anyway, let's look at the last question. This is May June 19, paper 2-1. You are asked to define velocity In the next revision video, I'll talk about the definition. Again, very briefly, I'm just rushing through this to let you know what you should know. Okay, does that make sense? Anyway, this is rate of change of displacement. So now you're asked to calculate K and you're given an equation. And take note in this table, instead of giving you the absolute uncertainty, you're given the percentage uncertainty. Once you're given the percentage uncertainty, it's a very easy question. Okay, anyway, just based on this one, I'm going to rearrange the equation a bit. So I'll square both sides. So V square is Kp over rho, and K is V square rho over P. And they're substituting the values right now, making sure everyone there is SI. Now, the reason why I'm rearranging it is to prevent errors, okay? And also so that I can write the absolute uncertainty and the percentage uncertainty better. So when you substitute, just double check the units, okay? Make sure everybody is SI. And if you rearrange, you can write the identities for uncertainty better. So generally at this level, I'll write a little bit more SF lah, in case I need it for the part 2, but I might not. So if you look at this equation, right, the uncertainty in K over K is due to 2 times uncertainty in V over V plus uncertainty in rho over rho plus uncertainty in P over P. So again, we are totaling up the percentage uncertainties. But this one, wow, magic leh, they gave you the percentage immediately, so you don't have to divide anymore. Don't have to divide, just write the percentage. So 324%, so 342% respectively. You just copy in the values, don't worry. So the percentage uncertainty is 12% of K. So now I can find delta K, 12% of 1.42. 1 SF, so 0.2. So this one is 0.2. So you're going to write, okay, so yeah, make sure the decimal point, the SF will fit, okay? So 1 dp, sorry, 1 SF, and the dp follows the SF. All right, so yeah, that is uncertainty. Go try more questions. I'll see you in the next video for revision 2.